Maybe let's do a quick check. Any issues with the lab report? Any questions?
When you ask
Sorry to interrupt your hair. There, what?
when you ask to put the calculations in the lab report,
Yeah.
do you want us to like label like, oh, this is the calculation for red RF, and then put it there? Or?
One type of each calculation. So you don't have to do, show me an RF for yellow or blue or red. Just show me an RF from your data. So any different calculation, so for example, that follow-up question, separation distance, that's more than just an RF calculation. So show me that.
Oh, okay.
So one of each, and as long as it's clear that it's a calculation in a section for calculations, it's fine, all right? Remember, one report per group, one data table per person. Don't make the data tables page one. First thing I want to see is not your data table. I want to see title, name, and your partner's name, date, block, objectives, and then if you want, see data table under data and observations, but don't make your data table page one, all right? Any other questions? Now, if some questions surface between now and Thursday, which is when I see you next, we're all here Wednesday, not in class, but I'm here, you're here, find me Wednesday if there's still some last minute issues you think you need to solve, all right? If you're going to write out the report by hand, which is fine, obviously I need to be able to read it, but don't give me a report in pencil. Data table in pencil is fine, but give me a report in ink. If you want to type it up on a computer, that's fine too. Just make sure the data table you fill in with my initials is the data table you turn in for the lab report. Okay. What I want to do today is begin and move as quickly as we possibly can through section 2.4. Moving quickly because most of it is a review. The only part of section 2.4 on chemical formula writing and naming that isn't a review is compounds that we refer to as hydrates. And they're kind of an interesting combination of ionic and covalent. It's not hard, we just haven't done it, okay? Also, there's a few things that I need to correct in terms of Gary's attempts to simplify things, and I will attempt to do that wherever those concerns surface. Section 2.4 is not a long section. That's intentional because the understanding is you've seen this before. But as I've said several times, because I didn't teach most of you last year, and also because it was a long time since we talked about formula writing and naming in grade 10, you may have to remind yourself of some of the laws, the rules, all right? Why are you here without it? So if you look at the warm-up, Gary doesn't ask you to do it, but by way of practice, you can name every one of those compounds that are on there. Notice that some of the compounds are binary, which means two elements. For example, that's a binary compound. Some compounds aren't binary. They're not binary because they have polyatomic ions. Notice some compounds, if you wanted to name them, have to have Roman numerals in their name. For example, that is not tin sulfate. There's no such compound as tin sulfate. That's tin 4 sulfate. Now, where are you going to get all that data? Not just to write the formulas, but if you wanted to name it, table of ions in your book. Not this table, that's a periodic table. Your table of ions, as we've referred to before, the back side of the second last page. You're going to get that from now on all your tests. The positive ions or cations on the top, listed alphabetically by name. The negative ions are on the bottom, listed alphabetically by name. And notice that data table says of some common ions. Not all the ions are on there. There's a lot of ions that aren't on there. But any polyatomic ion that you'll be expected to know the formula for or name is on there. But remember what I dictated to you, I don't know, maybe a couple weeks ago. predicting ion charge from position in the periodic table, which basically boils down to if an element is close enough to being like a noble gas in terms of number of electrons, it will give up or gain as many electrons as it needs to be like the noble gas. So for example, if you look on that table, look on the top part, do you see strontium? Look on that table, table of ions, back of the book, back side of the second last page. Do you see strontium on there, on the top half? No. Strontium's right here. If strontium's in group 2, it gets the same charge as every other metal in group 2. 2 plus, 2 plus. Is beryllium there? 2 plus? Alphabetically. Is beryllium there? But it's here. My point is, if you know what magnesium and calcium and barium do, you're 100% justified to say, well, gee, beryllium and strontium would do the same thing. Why do they do the same thing? Because if they lose 2 electrons, they become like the nearest noble gas. That's what I dictated to you folks. Okay? So if there's an ion that isn't on the table, but is within 3 of a noble gas, you should be able to predict its charge. For example, negative ions. Is selenide on your table? It's a negative ion. Well, what charge would a selenide ion have? Well, it's an oxygen group. Oxide is there, 2 minus. Sulfide is there, 2 minus. Well, then selenide's going to be 2 minus. It's got 34, it wants 2 more. Tellurium, it's got 52, it wants 54. Telluride is 2 minus as well. That's the idea. Arsenic isn't on your table. The arsenide ion isn't. But nitride is. Gets 3 electrons, so will arsenic. That's the idea. Now, I'm not going to expect you to know the names or charges of polyatomic ions. The only ones you'll need to know are on the table. But for single atom ions, like strontium, or beryllium, or selenide, or telluride, you can look at the table and accurately predict their charge because you know something else in that table has the charge, and that is on your table, okay? Now, you guys know that when you write formulas for ionic compounds, the formulas have to be in the smallest whole number ratio. The reason that is because, and I dictated this to you as well, there are no neutral independent molecules in ionic compounds. The formula is just a ratio. So you always have to reduce it to the smallest whole number ratio. As far as naming ionic compounds, 100% of the time, you name the positive ion, that's the first word. You name the negative ion, that's the second. That's it. Okay? So for example, if you look at this one that Gary has done for you, what's the name of that compound? Well, NH4, 1 plus, is ammonium. That's the positive ion. That's the first word. You always name the positive ion first. So the first word in that 2-word name is ammonium. The second word is oxide. Why? Because that's the ammonium ion, that's the oxide ion. Done. No prefixes, no di, tri, tetra. That's covalent, not ionic. Here, the name for that compound is tin 4 sulfate. Why? Because the name of that ion is tin 4. Now you're looking and you go, how would I know I need a Roman numeral there? Well, look on your table of ions. Look at the top half. And remember, metal ions are always positive. Tin is present in 2 places, with a 2 plus ion and as a 4 plus ion. And you remember from Science 10, those are multivalent. So if you see tin, you can't just say tin sulfate. There's no such ion as tin. It's tin 2. We used to call it stannous, and there's tin 4. We used to call it stannic. And if you look in your table, you see that written second. That's the old naming scheme. So write it with the Roman numeral after it. So that's tin 4 sulfate. You know it has to be 4 plus, because each sulfate is 2 minus. And if you need 2 of those 2 minus ions to cancel the charge on this charge must be 4 plus. Okay? so tin 4-sulfate. Notice, you don't need a Roman numeral for aluminum, because it always, 100% of the time, is 3 plus. And you look at your table and go, gee, why would it be 3 plus? Look at where it is. It's way over here on the right. Well, it's got 13 protons, which means it's got 13 electrons. So if it gives away 1, 2, 3, it looks just like neon. So that you can predict the charge, but it is on your table. But because it's never anything but 3 plus, you don't need a Roman numeral. The only time you need a Roman numeral is if there's a choice and those multivalent ions are on your table. And you don't have to learn any of the ones beyond what's on your table. Okay? Now, he doesn't ask you to name these, but it's maybe not a bad idea if some of this is a little rusty, or if you know last year in Science 10 for chemical formula writing and naming you had trouble. Mr. Dawson and I always wonder what it is about formula writing and naming that challenges students so much. We still don't really get it. Here's your table of ions, write the formula. Name the ions, name the compound. It's that simple, okay? I'm going to have to correct a few things Gary says here. Recall that nonmetals form, cross that out, right, covalent compounds. As you already know, they're not all molecular, but most are. Nonmetals form covalent compounds with other nonmetals. And then write, but they usually form ionic compounds with metals. Not always. But they usually form ionic compounds with metals. Meaning, if a compound's ionic, if a binary compound, a 2-element compound, like sodium chloride, if a 2-element compound is ionic, it has to be metal non-metal. But just because it's metal non-metal doesn't make it ionic. Most of the time it does, but not always. And this is the example I use last class. Remember, what dictates whether it's ionic or not is the difference in the electronegativities. And those numbers are on your periodic tables. So aluminum has an electronegativity of 1.5. Sulfur has an electronegativity of 2.5. That difference is only 1. And yet, that's a metal and that's a non-metal. When the difference is more than 1.7, the bond is considered truly ionic. But that difference is only 1. So technically, it isn't an ionic bond, even though that's a metal and that's a non-metal. Now, I mentioned sodium chloride. If you pick an alkali metal and a non-metal, it 100% of the time it'll be ionic, because something on the far left has a really low electronegativity, something on the far right has really high. So chlorine is 3.0. What's sodium's? 0.9. That's 2.1. That's clearly ionic. So if you're pairing a metal from the far left with a non-metal from the far right, you're guaranteed that the electronegativity difference is going to be more than 1.7. But if the metal's pretty far to the right, just because it's with a non-metal doesn't mean it's going to be ionic. Another interesting comparison is water. Clearly covalent, clearly molecular. Hydrogen's electronegativity is 2.1. Oxygen's is 3.5. That difference is more than with that metal and non-metal. So the bond in water between the hydrogen and oxygen is closer to being ionic than the bond between aluminum and sulfur. So anytime Gary says always or never, you gotta be careful with those words in chemistry, right? And case in point, the name of any ionic compound is simply the name of its constituent metal ion followed by the name of constituent non-metal ion. No. Put the word binary in front of ionic, the name of any binary ionic compound. Is simply the name of its metal ion followed by the name of its non-metal. If it's binary, then this statement is true. But it's not true for any ionic compound. Case in point, do you see a metal in that ionic compound? No. Not a binary compound. The name is ammonium oxide. That's a bona fide ionic compound, yet that violates this. But as soon as you put the word binary in there, 2 element, then it's true. But it's not true for any ionic compound. I think he knows that. I just think he's trying to simplify it, but almost all the time when he does that, he turns what is usually true into something that isn't always true. Whenever you name ionic compounds, name the positive line first, negative line second, that's it. No prefixes, no di, tri, tetra, penta, none of that, because the formula is just a ratio. Okay, and if you don't reduce it to the smallest whole numbers, then it's wrong. So for example, if you were going to write the formula for the compound between tin 4 and oxide, the 2 goes there, the 4 goes there. You guys have seen that before, right? You're going to get SN2O4. But if you leave it like that, it's wrong. Because the formula is only a ratio. So now it's correct. And if you look at the formula and want to name it, start with the negative line. Oxide's always 2 minus. And if 2 of them cancel the charge on a tin, the tin must be 4 plus. Which means the name of this compound is tin 4 oxide. Okay? And again, that's kind of review of Science 10. Here's another example of Gary's weird rabbit holes. You can cross this out after I read it. The different types of electrical charge are called opposite charges, okay? Because they have opposing effects. They can cancel each other. Everybody's fine with that, okay. But then he goes, note that there's a difference between canceling 2 things and 2 things canceling. What the? Canceling 2 things, example, magazine subscriptions, means eliminating them. By contrast, 2 things canceling means they negate each other's effect. Who the hell cares? Oh my God. You guys get the canceling, right? Done. Move on. Unbelievable. So, is this new to any of you? It's interesting he uses aluminum sulfide, which technically isn't ionic, but that's fine. Notice when you write it like this, it's already in the smallest of 2 ratio, so you don't have to reduce it. How many pages did we turn on? Okay. The computer's a little slow. Did any of your parents make appointments during the Zoom time with me? Yeah. For the first 25 minutes, no one showed up. 0. I'm waiting for parents, and I'm thinking, hey, no parents, which isn't a bad thing. And I'm looking at my computer, and I hear everyone else's, and I had a whole bunch of parents. So finally, Mr. Mesa comes in, and he goes, oh, I'm not sure what's wrong, and he fixed it temporarily, and it worked for 3.5 parents. But right in the middle of the 4th interview, your session is ended. Do you want to upgrade? No. And then it broke for the rest of the time. So, yeah, it was frustrating. Last year didn't work at all for 2 hours. So I talked to Mr. Olson about it. He doesn't know what the problem is. He said it might be a Zoom issue, but it always happens to me. Anyway, if your parents are one of those people that try to get on and couldn't, my sincere apologies. If they want to contact me, I've arranged, for example, today, there's 3 phone chats I'm going to have with parents. Because it's difficult to arrange schedules to do personal interviews or even Zoom if they're on schedule. Okay? this is true, all compounds are neutral. There's no such thing as a charged compound. And that's why the charges have to cancel. Okay? The formula Al2S3 means there are 2 aluminum ions for every 3 sulfide ions in that crystal lattice. Now, in this example, notice when you crisscross the numbers, leave the charges there, but crisscross the numbers, they're already in the smallest ratio. But if you connect a lead-4 cation to a sulfide anion, you have to reduce it, okay? You also know about multivalent elements. Some elements have 2 or more possible valence shell electron configurations. Yeah, that's true. These are usually relegated to the transition metals. These, okay? And we're going to learn a lot more about why they're kind of unique. In a nutshell, every element in the same family has a similar outer electron arrangement. For the transition metals, sometimes that's not 100% true. But something else that's true about the transition metals, in addition to having outer electron shells similar, there's also similarities left to right. So, for example, in this period here, scandium to zinc, most of those elements have 2 electrons on the outside, even though they're not in the same family. And that makes transition metals a little different than group 1 and 2 and the group 13 to 18, okay? Why is that? Well, when we talk about quantum mechanics, you'll learn why. And the reason why is also, which you'll learn, is one of the reasons we broke the periodic table up into these 4 blocks, okay? That means something to events. Anyway, you'll know if a metal element is multivalent because you'll see it twice on the table, which means when you're naming that, you've got to use Roman numerals, okay, in the name. Gary says here, a different method for naming the ions of multivalent elements was used in the not too distant past, and you may encounter it occasionally. And in your table, that's where it says comma and then something. Us or ick. So for example, tin 2 and tin 4 used to be stannis and stanic, was added to the root of the element's name from which the symbol is derived. The OUS suffix denoted the lesser ion charge, the IC denoted the greater ion charge. Okay? But use the Roman numeral. That's the moderate, okay? And that's the one that comes first. Now, I don't know that any of these sample problems couldn't have just as easily been asked or answered in grade 10, but what is the formula for tin 2 sulfide, or tin 4 sulfide? Write the symbol for the positive ion, negative ion, crisscross the numbers. So there's tin 4. Notice the second word, that's the second ion, tin 4 sulfide. The 2 goes there, the 4 goes there. So initially you get this, but you have to reduce it to that. Nothing to it. And again, that's grade 10, maybe even grade 9. And in addition to here's the name, what's the formula, it's also here's the formula, what's the name. Iron appears twice in your table as a 2+ or 3+ cation. A lot of students will look at this and go, okay, iron 2 sulfide. What's in Roman numerals has nothing to do with the number of the ion in the formula. It's the charge on the ion. So when you write iron 2, you're meaning the ion charge is 2+. It isn't 2+ here. If you're looking at a multivalent metal and you're not sure what charge it is, go to the negative ion and work backwards. So if you see Fe2S3, iron can be either 2+ or 3+. Start with this. Each sulfide is 2-. So that means that that part of the compound is contributing 6 negative charges. This has to be 6 positive charges, which means that can't be 2+, Because if each iron was 2 plus, this would only be 4 plus. If 2 iron cancel the charge on 3 sulfide, that must mean that each iron has to be 3 plus. So this is iron 3 sulfide. You might be surprised though how many students, when they're stressed or tired or running out of time, will look at that and go, iron 2 sulfide. That's not the way it works, okay? Now, because I didn't teach most of you last year, and I've made this point repeatedly, I don't know how much you struggled with formula writing your naming. Only you do. And that's why wherever there's practice, try them and check your answers each time, all right? Look at the practice problems at the top of the next page. So real quickly, why don't you guys do those? I know you're sitting next to each other, and I know there might be a tendency to check your answer with somebody else, and that's fine, but what if you pretended you were on a test right now? The only thing you're gonna get is your table of ions and your periodic table. Could you get the right answers? And I'm asking you to do that because even though you've seen this before, it was a long time ago, and I'm also suggesting when you're at home, do that. Do them and then check your answers. If it seems like I'm going pretty fast, it's because I'm going pretty fast. We have shortened blocks today, even more than normal, because not only for the Mass, but for the Remembrance service. Is somebody's phone? See, that's why I say turn them off. Don't just put them on silent. So this block ends, and we still got about 23 minutes, so we'll probably still be okay. All of these are binary compounds. Okay, there's no polyatomic ions. Some of the names require Roman numerals. And again, that's close to being science 9 or science 10 as you can get. Yep.
Do you care if sulfur is with pH or F?
I would prefer pH, it's just that I think the book might use F. Yeah, the book uses F, but old school pH. Takes two of you guys to hand out that?
Yeah.
Okay. Unless somebody really wants to do that, Kim. Okay. Any questions on that? Good. Let's add yet another level of complexity, polyatomic ion. Now I gotta make a couple corrections here as well. Recall that a molecule is a neutral group of covalently bonded atoms. That's true. A polyatomic ion is a charged group of covalently bonded atoms. So it's like a molecule except it has a charge, which means it's not a molecule. The correction I want to make here, a polyatomic ion is a charged group of covalently bonded atoms. Well, most polyatomic ions are. Most polyatomic ions, if you look in your table, have nonmetals bonded to oxygen, okay? And if there's nonmetals bonded to nonmetals, the bonding inside the ion is covalent. So for example, nitrate, nitrogen and oxygen, sulfate, sulfur and oxygen, phosphate, phosphorus and oxygen, chlorate. But notice there are a few polyatomic ions that have metals and nonmetals in them, like chromate, chromium, dichromate, permanganate. So usually the bonding in the polyatomic ions is covalent because usually the polyatomic ions have only nonmetals in them. But not always. Sometimes you have metals and nonmetals, okay? Many polyatomic ions are oxyanions. All that means is they're anions with oxygen. I mean, here's an example. Nitrite, nitrate, sulfite, sulfate. Notice that a lot of series in the naming that have 8 and ite counterparts. If you have an 8 and an ite ion, the only thing it means is the 8 has one more oxygen than the ite. So sulfate has 4 oxygens, sulfite has 3. Charges are the same. Nitrate has 3 oxygens, nitrite has 2. Charge is the same. There's one series in your polyatomic ions where you don't just have 8 and ite, you've got 2 more in that series. And Gary gives them here. So if you look in the middle of this quartet, there's chlorate, chloride, like nitrate, nitrite. But there's also quite a stable ion of chlorine and oxygen that has only 1 oxygen. They all have the same charges, but this has 1 fewer oxygen than ite. So ite means less than 8. But less than ite, we have to add a prefix. So hypo, you guys ever heard of hypodermic syringes? Like if you get a COVID vaccine, that's a hypodermic syringe. Hypo means beneath the dermis of your skin. So hypo means beneath or less. So that means 1 fewer oxygen than chloride, hypochlorite. And because chloride has 2, hypochlorite has only 1. Also, 1 more than 8 is per. Per means beyond or more than. So chlorate, 1 more oxygen than ite. Hypochlorite, 1 fewer oxygen than ite. Perchlorate, 1 more oxygen than 8. Now those aren't the only series like that, but I think those are the only 4 on your table. Okay? occasion, we connect two ions into one polyatomic ion. There's a few examples of that in your table. So carbonate. Now there's no carbonite, but the name of that ion is carbonate. But there's also a stable ion where we stick a hydrogen ion to the carbon. And now we call it hydrogen carbon. And notice if you stick an H plus to a 2 minus, you get a 1 minus.
Yeah, go back.
It's correctly named either hydrogen carbonate or bicarbonate. The Bi really just stands for hydrogen ion added. And it doesn't matter which one you use. Okay? And you'll notice in your table, there's commas there. Hydrogen carbonate, bicarbonate. Hydrogen sulfate, bisulfate. Equal, either are equal. Now, there's an exception to that. If you look at, you see phosphate in your table? Now, if we stick an H plus to that, you might think the correct name is biphosphate. It isn't. It's monohydrogen phosphate. Notice there's no comma there and said biphosphate. The reason we can't just call it biphosphate is because there's another ion with phosphate, but it's got 2 hydrogens on it, and that's called dihydrogen phosphate. So we can't just say biphosphate just because there's a hydrogen ion. Because one of them has 1 hydrogen ion, one of them has 2. And that's why we use monohydrogen phosphate for this one. And if we stick 2 H pluses on it, then it's dihydrogen phosphate, and it's only 1 minus. Okay? You guys remember from last year that, actually, I'm glad you mentioned this. See this dichromate? That's the name of the ion. A lot of students will find chromate on your table, which is CrO4 2 minus. So this is chromate. And this is a different ion, dichromate, Cr2O7. But a lot of students, let's say you saw this formula. A lot of students will look at that and go, tin 4 dichromate. That is tin 4. But if you call that dichromate, it's wrong. They see the 2 and they go, oh, dichromate. No, that's tin 4 chromate. Tin 4 dichromate would be that, okay? But sometimes students, when they're in a hurry or stressed or tired, they forget you don't use prefixes like mono, di, tri for ionic compounds, okay? The only time you bracket a polyatomic ion is in the ratio if the ratio is other than 1 to 1. And Gary shows us here, because sodium is 1 plus, hydroxide is 1 minus, that's the formula. If you do this, it's wrong. It's easy for me to mark formulas and names because there's no part marks. They're right or they're wrong. On the other hand, if you combine calcium 2 plus with hydroxide 1 minus, now the formula has to have brackets. You can't write this. That says you got 1 calcium, 1 oxygen, 2 hydrogens. That is what you have to write for calcium hydroxide, okay? So you never bracket a polyatomic ion unless in the correctly written formula there is more than one of them, okay? Here's another example. Let's say you connected calcium to sulfate, okay? Now when you put the 2 there and the 2 there, you initially get this. But you can't leave it like that, because that means the ratio is 1 to 1, which means all the brackets and the subscripts disappear. And again, that's grade 10 science. But again, some of you may have struggled with formula. And it was a long time since we did it, okay? Actually, about a year ago. Now Gary gives you some more here. So let me go back for a second, because I think maybe there's something else I gotta correct down here. Somewhere in here, he says that the only polyatomic ion that ends in ide is hydroxide. That's not true. I don't remember where he says that.
It's like at the bottom, like if you see, it's like note that there are some exceptions to these naming conventions, the hydroxide
This
ions.
one here, yeah. Do you guys believe that that's true based on your table of lines? In other words, is hydroxide the only polyatomic ion that ends in I in your table? Look. No, what's the other one?
Sorry.
Cyanide, yeah, so obviously that's not true. Another thing, most polyatomic ions with oxygen end in 8. But that doesn't mean that just because it ends in 8, it's got oxygen. Can you find an ion in your table that ends in 8 with no oxygen? Very last one, bottom right corner. Starts with a T. Thiocyanate. Thio tells us there's sulfur in it, okay? Now, I know Gary knows this, I just don't know why he writes it, okay? I think the reason he got on Lionel's radar was because he wrote a book called Flex Book, I think for grade 12, chemistry. I never heard of it, but I guess Gary did. I think he might have sold it to some of his immediate family. But I don't know that it became in common use. And had Lionel not known Gary, I don't know that he would have been part of the writing team. He's not a dummy, he knows his chemistry, he taught it for many years in Summerlin. It's just that, I think sometimes he didn't get out of Summerlin enough. So, yeah.
When you're naming dichromate, if it's in a covalent compound, do you have to use it?
Dichromate in a covalent compound? It would never be in a covalent compound, it's an ion. Yeah, so if there's a charge there, it's not gonna be in a covalent compound. The only time you use prefixes is if what you're looking at is a molecule. Covalent, that exists as a molecule, okay? But you never use prefixes for ionic covalent. Okay? Now, as soon as I say that, the type of compound you guys didn't see in grade 10 are called hydrates. And they're an interesting combination of ionic and covalent. And they're coming up later. They're not hard, it's just something you guys haven't seen before. So here's the name right, the formula. Potassium's 1+, sulfite's 2-, nothing to it. That's the positive ion, that's the negative ion, 100% of the time. Ionic compounds have 2 words, okay? Here's the formula, write the name. Well, notice that chromium's multivalent. How do you know that? Because if you look in your table, it's present in 2 places. So now you start with the negative ion. HSO4, 1-, named either hydrogen sulfate or bisulfate, has a 1- charge. If 2 of them cancel the charge on the chromium, that must mean the chromium is 2+. So this is chromium 2, that's the name of the first ion, bisulfate. It's that simple. Now, we probably don't have time for you to do all of them and me write them on the board, but let's pick a couple. What about aluminum dichromate? Write the charge for the cation. There's aluminum 3+. Dichromate is Cr2O7 with a 2- charge. The 2 goes there, the 3 goes there. You get Al2 bracket Cr2O7 3. Okay? Notice you don't need a Roman numeral in the name because aluminum 100% of the time is 3+. And it's not dialuminum tridichromate, it's aluminum chromate because the formula is just a ratio. What would the name of F be?
Iron dichromate.
The name of that compound.
Iron 2 dichromate.
What's the first word of the 2-word name?
Wait, is it iron? Which means this.
Which iron? There's no iron called iron. It's iron 2. How do you know it's iron 2? Because there's one dichromate, which is 2 minus. So that's iron 2 dichromate. What's the name of C? Copper is also multivalent. So go to the negative ion. What's ClO called? Hypochlorite. And what's its charge? 1 minus. And there's 2 of them, right? So this is copper 2, that's the first word. Second word, hypochlorite. Okay? Copper 2, hypochlorite. Tin 2 oxide. Zinc hydroxide. No Roman numerals because zinc isn't multivalent. Sodium isn't multivalent. Sodium acetate or sodium ethanoate, but I think acetate is what you guys remember from last year. Now you might wonder, why do they write it like that? Why do they write CH3COO? Why don't they just write C2H3O2? Some junior textbooks write it like that. The reason they write it like that is kind of to suggest the structure. So the acetate anion looks like this. The reason they don't write the 2 carbons together is because they're different. One carbon has all the hydrogen stuck to it, the other carbon has the oxygens, and then the whole thing has a -1 charge. Okay? We'll talk about naming acids a little later on when we get into near the end of this section. Okay? We did it last year, but again, it's probably rusty. Names and formulas of binary molecular compounds. That's a fine type. Okay? If it's a molecular compound and it's binary, we use prefixes. Binary means 2 different elements. Molecular means it exists as a neutral independent species. Now we can't write ratios because the formula doesn't represent a ratio. It represents the actual number of atoms stuck together in the molecule. And in grade 10, you were introduced to the prefixes.
Do it after school.
I think somebody downstairs is saying, you're going to trim the foliage, do it after school. The prefixes that we employ are necessary precisely because the formula isn't a ratio. And in grade 10, we probably gave these to you.
Excuse this interruption.
You have to
In a moment, we'll begin calling down classes for our Remembrance Day Mass and service. Just a reminder, we're asking our community to be reverent as our gym transforms into our church, a sacred space. As you are processing into the gymnasium, we will be playing our Fallen Night slideshow for our guests and for our community. And it's very important that you're reverent and quiet as you enter the gym. At this time, we ask for all grade 8 students and their teachers to please come to the gym. All grade 8 students. Thank you.
I don't see you guys till next Thursday, but once again, if there's an issue with the lab report, find me Wednesday. I'm probably on Google Classroom, going to ask you to the end of this
Share
session.
you the document.
You'll be introduced to hydrates, and unless I'm mistaken, I think Gary also discusses naming acids. Yes, he does. There's only a few more pages to read. Hydrates have an ionic part and a covalent part. It just means the ionic part has a bunch of water molecules stuck to it. And because it's molecules, you need prefixes. So the first part of it's the ionic rule, and the second part's the covalent rules. But I'll teach that on Thursday. I can finish 2.4 for sure on Thursday. 2.4 finishes chapter 2, which means not next week, because I only see you guys once, but probably the tail end of the next week might be a potential time for our second test. As far as I know, I think it's sufficiently prior to the report cards that I'll have another test mark for the report cards. We'll do our best, okay? And remember, next to tests, lab reports count for the most in terms of grades. Yeah, go ahead. Go ahead. Let's see if way better. Any of this problem for you guys? You okay so far? It's going to take practice. It's not hard, but it takes practice. All right? Something that I mentioned to your parents, I had a couple of parents, they showed me their phones and they said, look, your mark is the lowest mark they're getting. And I went, yeah, okay. Would be. Like, maybe this is a little harder than some of your courses. I suspect that it might be that, coupled with the fact that I might expect a little more of you than some of the other teachers. But that's what the course is about. Okay? So don't get overly bent out of shape if your mark isn't as high as it was this time last year in grade 10. Okay? And I said this to the parents dozens of times. For those who are able to get in. If you guys stick with it, keep working hard, pay attention to what I tell you. As common as it is for the first mark to be lower than what you're used to getting, it's also common for your final mark to be as high or even higher than it was in grade 10 summer. I know you don't believe me because you're going through this for the first time. That's not to say some of you aren't doing really well, some of you are. But if you're not doing as well as you did in grade 10, it doesn't mean you're stupid or got stupid over the summer. It doesn't even mean the course isn't for you. It just means it's going to ask more of you than what we asked of you in grade 10 in junior science. Okay? So have faith. And if you doubt that, ask Amelia. She'll tell you. Okay? The first test in Chem 11 was not overly encouraging for a lot of grade 11s last year. But if you talk to them and find out what mark did they end up with in grade 11, then they'll tell you that the first was a little bumpy, but then it got better. And I wouldn't say that if it was a lie. But I've been doing this for a long time, and it's a common thing. And rather than, there are some students for whom this course, they're just not cut out. I'm not saying that everybody can do great in Chem 11. But I don't think most of you have been challenged yet. And because of that, I don't think most of you know what you're capable of. And that's one of the differences in chemistry. You not only learn a whole lot about chemistry by the end of the year, you learn a lot about yourself, what you're capable of, and even what you're interested in. So, yeah, the sky isn't falling. Just stick with it. You've only had one test, all right? And if you do it well in your lab report, the mark's going to go up because it counts for well, okay? I'd like to think that by the next parent-teacher interviews, I don't think they happen until the late winter or early spring, that we can look back on this and go, well, you know, it wasn't that good before, but now it's improved.
And we would like to call down the grade 9s. Grade 9s, please come down to the gymnasium.
So you guys can play amongst yourselves.